Okay, so let's start talking about proof rules. So basically, in Hoare logic, the idea is that you need some way of reasoning about each different kind of construct in the language. So in this IMP language, we're really talking about reasoning about statements, commands. So what we're basically going to have to start with is a form of reasoning about each different kind of statement that we can have. In the form of valid Hoare triples, and some extra rules that help us make proofs a bit more convenient and so on. So the rest of this lecture is actually about these proof rules and how we use them. We'll start in this segment with the rule for assignment, which is in some sense the most important, most fundamental rule, because it's the one that talks about how variable values change, and because Hoare triples are all about states and predicates that hold in states, then it's all about the variables. So reasoning properly about the changes in variable values is key to everything. Okay, so if we think about assignment in IMP, we've got this sort of situation here. So we've got some assignment of y to some variable x, and we know something, say, about y beforehand, then we can use that to conclude something about x afterwards. So this one is pretty simple. So if we're assigning y to x and we know that y is 1 beforehand, then we definitely know that x is 1 afterwards. Okay, so this is an instance of assignment that we would want to have, but that's not the only instance, right? This is a very simple situation. So here's a slightly related one where we're, instead of assigning to a single variable, we're assigning to some expression, and we happen to know that beforehand that expression is 1, then we know that x is equal to 1 afterwards as well in this case. So the first version of the assignment rule that they give here is that if we have some arithmetic expression a, and we happen to know that expression is equal to 1 beforehand, then we know that x is equal to 1 afterwards. Okay, but this is a very specific case still as well, because it's only talking about equality to 1 and so on and so forth. So the form of the rule that we actually get is this one, which says that the sort of key to it all is the assertion that holds after the assignment has happened, and we can use the components of the assignment to get the assertion that must have held beforehand if Q is to hold afterwards. Now there's a bit more stuff going on here. So what is this square bracket arrow notation here? It's basically saying that you take the assertion Q, and throughout Q you replace all the x's with a, right, where x and a come from the assignment statement. Okay, so in essence what you're saying is if the assertion Q holds beforehand about a, then it holds afterwards about x. That's the one way to think. So Q is going to talk about x, presumably. If you think about what needs to hold before, it has to be that same property has to hold for a, replacing every x. Okay, so that's so you're sort of reasoning backwards here, which we'll talk about reasoning forwards a bit in a minute. So if we have a look at this one, for example, if we've got x is x plus 1 is the assignment, and afterwards we want x to be less than or equal to 5, then what we have beforehand is x less than or equal to 5, so that's the Q, and we're replacing all the x's by x plus 1. So what we've really got is x plus 1 is less than or equal to 5, which is the same as saying x is less than or equal to 4. So that makes sense, because if x is less than or equal to 4 and you add 1 to it, then afterwards you know that it's less than or equal to 5. Okay, And this takes care of the sort of x being updated, right? So it's not just assignment. So this one is just a simple assignment, which is saying afterwards we want x to be 3, and the assignment makes x 3. So when we do the substitution of x becoming 3 in x equals 3, we get 3 equals 3, which is true. So the precondition here is true, which means it means the starting state doesn't matter. We do the assignment, we always get x is equal to 3, which again makes sense. It doesn't matter what the value of x is or any other variable. If all we're doing is assigning x the value 3, then afterwards we definitely know x is 3. And the substitution sort of makes it clear that that's what's going on. And this is a similar example. A couple of x's in here, so you have to substitute both of the x's to be 3. This formula is true as well. Okay, so that's the sort of idea behind assignment. In this is often called a backward reasoning rule. So you're starting with Q, which is the postcondition, and you're reasoning backwards through the assignment to get what the precondition needs to be. And if you do this in a sequence, essentially if you do this sort of reasoning in a sequence, as we'll see later, you end up with a predicate, an assertion for the beginning, with what has to hold when the program starts running for the final assertion to be established. Okay, so how are we going to formalize this? Well, we can sort of take that idea of substitution. Now, if you naively sort of think about it, what you really want to do is take the assertion as a syntax tree or something, and you want to go through the syntax tree and find all the x's or whatever and replace them with the expression that you're substituting in. We can't do that in this case because the assertions are just arbitrary, are built out of arbitrary Coq propositions, so we don't have an AST for them. It's just an expression in the language. So the way they formalize it here with this assignment substitution thing, so again it's taking the variable x and substituting all the x's for with a in the assertion p. So the way they do that is by constructing a new assertion, which is p, but where the state that we're applying it to has x updated to be the value of a. Okay, so this is equivalent to the textual substitution version that we might otherwise have used. And the notation that we've been using in the examples is just a shorthand for a use of assign sub in the obvious way. So I'll let you have a look at the example here, which basically just explains a bit more about that. But the essence is that you just use an updated state to evaluate the assertion when you're doing the substitution. So where's this leading? Well, that basically leads us to this proof rule, which is called Hoare assign, which is this. It basically says it's an axiom, so it's an axiom schema, I guess. There's no assumptions. So if you have an assignment x is a, x becomes a, and you want to establish q, then the precondition is the substituted version. Now you can think of this whole thing here as a triple, right? It's a precondition, a command, and a postcondition, right? But it's basically saying, as long as you fit into this format, this syntax, then it's always true. But just because we've written it down in a comment here doesn't mean it actually is valid. This is a proof that that this is logically the case. Okay, and it basically hinges on. If we go to here, right? So we're in this position here where we know that we can start in state st and run the assignment, and we end up in st prime. We know that the precondition holds in st, and we need to show that that implies that the postcondition holds in ST prime. So the first thing to do is to basically take advantage of the fact that we know this is an assignment. So it tells us a relationship between ST and ST prime. So if we do an inversion there in the subst, we basically now have that ST prime must be this state, right? Because that's what the evaluation relation says for assignments. And we can then simplify the substitution here using an unfold, right? And lo and behold, you notice that the state that's being applied to Q, that Q is being applied to here is exactly the state that we had up here, and so now we've got the HQ is exactly what we want to establish the postcondition. Okay, so it's important that you sort of understand the two parts here. So this rule is, or this schema, right? It's because it's instantiated by 3 variables, but this is an instance of this assignment rule is always, we've just proven that it's always valid. It doesn't matter what Q, X, or A are. This rule always holds for any combination of those things. So this is a very powerful proof rule. And in order to use these proof rules in our proofs, we want to make sure they're actually valid proof rules. Otherwise, we're going to lead to conclude things that aren't actually true. Okay. So this is just a very simple use of that rule to reason about assignment of X to 3. It's a very interesting proof. Okay, so we're sort of working our way through here. We're sort of in this part of the lecture. Now, one thing that may be occurring to you is when you're thinking about this, it's actually a little bit hard to understand what's going on here, because when you're thinking of running, what programs do and things, it's more natural to think in a forwards direction. In other words, if I know certain things and then I run this command, in this case an assignment statement, what do I know afterwards, right? Whereas this proof rule that we've got is really reasoning backwards. It's really saying, well, if I want Q to hold afterwards, what must hold beforehand? Okay. So it's deriving a precondition from the postcondition rather than the other way around. So what they talk about next in the book here is other versions of this, which are more in the forwards direction. So for example, this version here says, well, if under any circumstance we have, in other words, in all states, if we assign X to A, or A to X, then afterwards we know X is equal to A, which seems like it should be true, right? But as we saw in an earlier chapter, I think, it's not necessarily true if A includes references to X, right? Because the A in the assignment statement is using the, so imagine this was X becomes X plus 1, then the X plus 1 is using the old version of X, but when we write it in here, if we said X is equal to X plus 1, well, that can never be true, right? Because somehow the old version of X and the new version of X have now been conflated rather than being kept separate. So this doesn't work. This is sort of a naive, simple version. It turns out that you can actually write a forward version, which is this version here. What they do basically is they say, well, the way to sort of keep track of the old version of X is to use another variable. So here there's an assertion that's saying that, well, the value of X in the initial state is M, some M, which you can then use in the later thing. So the thing that's going on here is that you're saying, well, P holds in the initial state, P also holds in the final state, right? And it's P holds in ST prime, which is in this case, the ST here with X being M, which is what we knew its initial value was. So in other words, P is the precondition still, right? So it's holding with X being M, which is the initial value of X. So that avoids the problem of forgetting what the initial value was. And STX equals the evaluation of A in the state where X is M. Right, so this does actually work, and you can prove this, and in fact you have to prove that for your homework, right? So this is a statement of the stuff that's in the comment here, with an extra functional extensionality assumption, which they sort of note that you're going to need at some point. So you can prove this this rule, and it is valid, but it's a bit more complicated than the backwards rule. So this is one rule for reason for why people don't tend to use it as much. It does get used a little bit. And another version is this one here, where instead of having a previous value of X sort of indicated in the precondition up here, there's an exists in the post condition that says, well, there is some value of X, some value M, which X has beforehand, and the updated version makes everything work. So again, this is a more complicated version of the assignment rule to enable you to reason forwards. So typically, in most uses of Hoare logic, people prefer to reason backwards, and another reason for preferring that actually is if you're reasoning forwards, you're sort of generally saying, well, if I start with true, in other words, I start in any state, I can sort of push that through and I end up with a formula for what assertion holds at the end of the program. But what you mostly want to do when you're doing verification is you've got an assertion that you need to hold at the end. And so you're given the assertion, what property has to hold for this program when it's finished, right? In other words, what holds for the things that it computes, for example. And so you've already got the post condition. So it's more natural to sort of say, well, if I'm aiming to get that post condition, then what preconditions do I need all the way through? If I can push that all the way backwards and get true at the beginning, then I know it doesn't matter what state I run the program in, I will establish the post condition that I want, which means that the program in that sense is correct. So in many applications, the starting with the post condition and working forwards is just what you want. Okay, so that's the assignment rule. I'll stop there and pick up in the next part with some more rules.